be talking about optimization, which is a lot different than curve sketching, which is what we just did, um, but it's still equally important. This has a lot more applications we'll see. I seriously hope my iPad can survive through this because it's on low battery. But let's see. I'm just going to give you, similar to curve sketching, I'll give you some tips, then we'll dive headfirst into our problems. So here are my tips. First, identify quantities that you're given and what you want. Second, which should actually probably be first, you want to sketch the problem if it's possible. A lot of times this will have to do with things you can visualize, shapes or real world scenarios. So sketching it can be really helpful. Only do that if it's possible. If not, you don't want to be wasting so much time. Next, you want to write the equation for the quantity to be minimized or maximized. We're talking about optimization, so that usually has to deal with how do we maximize some quantity or how do we minimize something. Think about it. If we want to optimize, that's not a good example, but it really has to do with maximization and minimization. So we can see that stuff that we learned about extrema, how getting the first derivative, setting it equal to 0 to get our minima and maxima, that's going to come in handy. And here, usually we want to maximize volume. This is just the types of problems we normally see. So that could be like also area. So for these, you want to use your geometry, make sure you're familiar with your equations. After you do all that, you're going to want to develop a secondary equation to get the information given. This might seem a little bit confusing now, but as we do some problems, it'll make sense. Then you're going to make some substitutions into your primary equation. And then finally, you can solve for your maxima or minima by taking the first derivative and setting it equal to 0. Seems confusing, might be a little bit. Let's just do some problems. So it's so nice to see a question that's not, here's what f of x is, draw the curve. So here we have a manufacturer wants to design an open top box with a square base and surface area 108 square inches. What dimensions, square side length and height, would maximize the volume of the box? So maximize. That indicates we want to take the first derivative at some point. So we have a box. I'm going to do my best to draw it. Something like, nope, that's not going to fly. I'm pretty bad at drawing, so you're going to have to bear with me. So that's like a square base box. And then we have some height, which need not be the same as the side length on the bottom. And it's open top. So something like this. Excuse the drawing. It's very sketchy, but that'll work, okay? And it's open top. So the base is a square, so we'll give it dimensions x. And then we have some height, which I'll give it value h. And we're given that the surface area should be 108 square inches. So, given surface area equals 108 inches squared, goal is to maximize volume. Maximize volume. Okay, so in terms of the dimensions we're given, we should probably get equations for surface area and volume because those are the quantities that we're interested in. So surface area, that is equal to the sum of the areas of the 5 sides. Keep in mind there are 5 sides because it's open top. So let's start with the bottom side. That's this bottom square here. So that has area of x squared. So x times x. Now we'll consider these the upright sides. So this side here has height h, length x. So this has area hx. But before we write that down, let's look at this other side here. That has also length x and also height h. So that area is also hx. And similarly, the back one is hx, and this last side is hx. So this is plus 4 times h times x. So in total we get x squared plus 4hx, that equals 108. Okay, and then volume, that's your simple base times width times height. So this is equal to x times h. And we want to maximize the volume. So really, we want to take the derivative of this at some point. But taking the derivative of this seems kind of hard because we have two variables. And that would require like some implicit differentiation. And we don't really know how h is changing with x. That would be quite complex. But what we can do is, as I alluded to previously, make substitutions. We have an equation here, so we can solve for h, which will be in terms of x, substitute it into here, and then we have volume in terms of x. We can take the derivative, and we will be in great shape. So we have x squared plus 4hx equals 108. So let's solve for h. We get 4hx equals 108 minus x squared. So this tells us h equals 108 minus x squared, all of this over 4x. Beautiful. And then we can simplify this a little bit further. This is 108 divided by, do I want to do that? Yeah, no, I'll just keep it how it is. Oops. Okay, so we solve for h. Now, let's plug that into volume. Volume is equal to x squared times this 108 minus x squared, all of this over 4x. So that's 108x squared minus x to the fourth, all of this over 4x. Now we can simplify it just a tad, just by separating the fraction. And this will get, this is equal to 27x minus 1/4 x cubed. Great, so now we have volume equal to something as a function of our side length. And we're trying to maximize this, and we want to find the side length and the height. So if we take the first derivative of this equation here and set it equal to 0, we will get a potential maximum for volume, and solving for x will give us the side length such that that volume is a maximum or minimum. And then using that, we can solve for h because we have h in terms of x. So let's just do it. So the derivative of volume in terms of our side length x with respect to x equals 27 minus 3/4 x squared. Okay? And we want this to equal 0. So let's do that and solve for x. 27 equals 3/4. Oops, my battery is running low. It's okay, we'll be able to make it through it. We can multiply both sides by 4/3. We'll get this is equal to 36. So x equals plus or minus 6. And now we should stop. What is x? X we define to be our base side length. So can x be negative 6? No, because we can't have a negative length. That just doesn't make any sense. So we're going to get rid of that minus sign, and we'll say that x can only be positive 6. So we have the base side length. Now we need to find the height as well. So we know height is equal to 108 minus x squared, all of this over 4x. So we plug in 6 into here. This gives us 108 minus 36, all of this over 24. This is 3. So we are saying the volume is maximized for a box with dimensions 6 inches by 6 inches by 3 inches. And we sort of came to this claim quite suddenly. Like, we found values for the side length and the height, but we just said it's maximized. Do we actually know that to be true? Well, maybe we set it equal to 0, the first derivative equal to 0, but what if this is a minimum? So we would have to check another value just to make sure our claim is correct. So let's do it. Let's just do it. We just need to find one other possible value for x and h, and if that is less, then we know we found a maximum, and if the volume turns out to be greater, then we know we found a minimum and something went wrong. So let's just zoom in here. Let's let x equal 8, and then we'll solve for h. So we get 8 squared plus 4h times 8 equals 108. So 64 plus 32h equals 108. So 32h equals 44, I think. H equals 44 over 32. That's equal to 11 over 8. So we're saying the dimensions are 8 by 8 by 11 over 8. And if we compute the volume, we get 88. If we scroll back here and we compute this volume, we get 6 times 6 times 3. That's equal to 36 times 3, which is equal to 108. And that's greater than we just found, so we're good. We've found a maximum. Cool. So that's our first question. So that's sort of what I mean. Finding two equations, making a substitution, taking the first derivative, setting it equal to 0, computing that value, find your other value, and then check. Let's do another question. So an artist has 4 feet of wire and wants to form outlines of a square and a circle by bending the wire. How much wire should be used for each shape to enclose the maximum total area? So this will be a lot easier to draw for me. We got a square and we got a circle. Cool. And well, let's just give some dimensions. The square is x by x, and the circle has radius r. So we're bending the wire to create outlines. So that means the perimeter of these shapes should sum up to 4. So let's just write that out. The perimeters should sum to 4. So the perimeter of the square is 4x, and the perimeter of the circle is 2 pi r, and that equals 4. We want to maximize our total area. So area is equal to area of the square, which is x squared, plus area of the circle, pi r squared. And again, we want to maximize this. We want to take the derivative of that, but we have it in terms of two variables. So what we're going to do is make a substitution. So we can just choose our variable. I'm going to choose r to isolate for, and we'll see that, okay, 2 pi r equals 4 minus 4x. So that is equal to, and then we get r equals 4 minus 4x over 2 pi. We can do a little bit of factoring here, and we get that this is equal to 2 over pi times 1 minus x. So now we can take this for r and substitute it into here. So we get area equals x squared plus pi times 2 over pi 1 minus x, that quantity squared. Right? So this is equal to x squared plus pi times 4 over pi squared, 1 minus x quantity squared. And then finally, just a little bit of simplification here. So that's our equation for area. And we want to maximize this. So now we can take the derivative in terms of x, which is one of our side lengths. So the derivative of area with respect to x equals derivative of x squared, that's equal to 2x, plus derivative of this. This is a constant, so we pull that out. And then we take the derivative of 1 minus x squared. This will require the chain rule. This is 2 times 1 minus x times negative 1. So this ends up being 2x plus 8 over x. So I multiplied this 4 and 2 together, 8 over pi. And this negative 1 I'm going to distribute into here. So this becomes x minus 1. So that's our first derivative. And we're going to set this equal to 0 because we want to maximize area. So we get 2x plus 8 over pi x minus 8 over pi equals 0. Okay, so we can move the 8 over pi to this side. We can factor out an x, 2 plus 8 over pi. So this tells us x equals 8 over pi divided by 2 plus 8 over pi. That is approximately equal to 0.56. I'm going to add a page. All right, cool. So now we still need to solve for r. We had r equals 2 over pi times 1 minus x. So if we just do a little bit of a substitution here, this is 2 over pi times 1 minus 0.56 approximately. This is 2 over pi times 0.44. That should be equal to 0.28. Okay, so now let's just we should check our solution to make sure it is the maximum. So with x equals 0.56 and r equals 0.28, area equals, I'll just remind ourselves of the equation we created. So this is equal to 0.56 squared plus pi times 0.28 squared. And if you multiply this all out, we get approximately 0.56. So now we have to check some other value. And, well, what if I decide that, okay, I just want to use all of the wire for the square and not even create a circle? So that means all 4 feet go into the square. So the perimeter is 4x plus 0 because there's no circle, which means that x equals 1. So with x equals 1 and r equals 0, area equals x squared plus pi r squared equals 1 squared plus pi times 0 squared. That's equal to 1. And you're like, wait a second, this is greater than that. So this can't be our maximum. Not maximum. Okay. And now you're like, okay, this is not good. We just solved it for absolutely nothing. It's a wrong answer. And now you're thinking, okay, well, I said, what if we just put all of the wire for a square? Why don't we just put all of the wire for the circle instead? So, what if all wire was used for circle? Circle. Right? Then we have x equals 0 and r equals, well, we don't know what it is. We know that the perimeter is going to be equal to 4. So if we solve for r equals 4 over 2 pi, which is equal to 2 over pi. So then we say that area equals x squared plus pi r squared, 0 squared plus pi times 2 over pi squared. If you compute this out, we get approximately 1.273. You're like, wait, that's even larger than what we got before. And it turns out that this is your best choice. The best choice is to make only a circle. So, what's the lesson? Always check your endpoints. And in this case, endpoints doesn't really make sense, but you have to consider these like somewhat obscure cases, these edge cases, that here I decided I'm just going to use all of the wire for the square and none of the wire for the circle. So that's our lesson for these types of questions. You always want to check those. All right, couple more questions, almost done for today. It's a lot to do, but we're making progress. So now we have like a physics question. Position of an object moving along a straight line for t is greater than or equal to 0 is given by this equation here. And then we have a second object along the same line given by another equation. Both objects begin at t equals 0. At what time is the distance between the objects at a minimum? So we want to minimize our distance. So we have s1 equals t cubed plus 2. s2 equals t squared. And they're traveling along the same line. So how do we get distance? Distance, well, that should just be the difference between their positions. Because they're along the same line, and it's a line, so that's the straight line distance, so we can just take the difference of these two positions. Cool, so we have distance in terms of time, it's already in one variable, so let's just take the derivative of this. So we'll say the derivative of distance with respect to time, 3t squared minus 2t. We can set that equal to 0 because we want to minimize distance. Factor out a t. So that means either t equals 0 or 3t minus 2 equals 0. Immediately we can cross, well, maybe not. Maybe we can't cross out t equals 0. You know what, actually, we'll keep t equals 0. Here, when does 3t minus 2 equal 0? When 3t equals 2, t equals 2/3. So we have two potential times in which the distance is a minimum. So let's just plug both of them in and see which one is smaller. D of 0 is equal to 0 cubed plus 2 minus 0 squared. That equals 2. D of 2/3 equals 2/3 cubed plus 2 minus 2/3 squared. This happens to be approximately 1.852. So this is smaller, and we'll say that at t equals 2/3, the distance, nope, that's not how you spell distance, the distance is at a minimum. And we can check this, just take another point and see if it makes sense. Let's try distance at 1. 1 cubed plus 2 minus 1 squared. That equals 2, and it seems to be the case that that's correct. So, yeah, that was a pretty simple question because we were able to get that equation in terms of one variable pretty easily. All right, now we have a multiple choice question. So we have a graph of f of x and g of x. And I know it's in different colors, but this is one entire function. It's defined piecewise, and whoops, each color is the own piece of it. So we have h of x equals f of x times g of x, and we want to find h prime of 3. Spoiler, this has very little to what we've done in today's lesson. This is just a review of things we've done in the past. So if we have h of x equals f of x times g of x, then to compute h prime of x, that's just basically a product rule. This is nothing more than the product of two functions, so we take the product rule. First times the derivative of the second plus second times the derivative of the first. Okay, and we're computing h prime of 3, right? So h prime of 3 equals f of 3 times g prime of 3 plus g of 3 times f prime of 3, right? So these values, f of 3 and g of 3, those are pretty easy to compute because we just look at the graph. At x equals 3, f of 3 is 1, and g of 3 is 3. So let's just put those values down. 1 times something, 3 times something. Now we need to find g prime of 3. So we're somewhere here. G prime is the slope of the tangent line at x equals 3. Since this line is linear, that happens to be the tangent line. So we just need to find the slope of this g line, this purple line, not the pink one. So let's do that. We can take 2 points. We know 3, 3 is on the line. We can see that 0, 0 is on the line. So if we take the slope of that, slope is equal to 1. So g prime of 3 equals 1. Similarly, f prime of 3. We take a look here. The tangent line is this black line, so we just need to find the slope of this line. We know the point 3, 1 is on the curve. We know 0, 2 is on the line. So this slope happens to be negative 1/3. And we are adding these together. So this gives us 1 plus negative 1 equal to 0. C is our answer. And here we are, late at night, 6% battery on my iPad, 10:56 p.m. What a night it's been. Last question. It's just a simple multiple choice. We're given the graph of h of x, and we just want to find what could possibly be the graph of h prime of x. So for this, we need to look at our tangent lines and perhaps the sign of those. So when x is very negative here, the sign of the tangent line is negative. So we're negative, 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 negative. And still when x is less than 0, we reach a point where the tangent line is 0. Then we go positive, 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 and we get into positive values of x, and we're still positive until we reach a maximum, and then we have tangent 0, and then we go negative, 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 negative. So our graph should go from negative to positive to negative. So let's take a look at A. We're looking at graphs of h prime of x, so we should be looking at the y values and see if they match what we said. Here we go from positive to negative to positive, so that's not right. B, we go from negative to positive to negative, so this could be right. C, we go from negative to positive, but we don't go back to negative, so that's not right. D, we're always positive, so that's not right. E, we go from negative to 0 to negative, so that's very close to B, but remember, we had this huge section here where the tangent line was positive. The sign of h prime was positive, so this can't be equal to 0, so this is also wrong. B is our answer. That's going to conclude today's lesson. What a long lesson it was. I didn't expect it to take this long, but yeah, that is our brief review. Those last 2 questions were review, but the previous questions were about optimization. And as you saw, tons of real-world applications. Hopefully you enjoyed that little unit at the end there on optimization. I think it's a pretty cool topic. And yeah, hopefully that was helpful.